Alright guys, so this time I wanted to explore together Conway's Game of Life. Game of Life is a classic computer science problem, but the concept of how it works is very simple. We have a grid filled with square cells, and based on a few rules, we can decide whether the cell is dead or alive. First, any live cell with fewer than 2 live neighbors dies, as if by underpopulation. We can count the number of live neighbors by going through all the 8 adjacent cells of the current cell, and we can check which one is alive. If we have less than 2, the current cell will die next tick, but having too many live neighbors isn't good either, so any live cell with more than 3 live neighbors dies, as if by overpopulation. Imagine that if we do not cap the maximum number of neighbors, this will just lead to an exponential growth in alive cells, which will just fill the entire map with alive cells. So we need some sort of a balance. And lastly, any dead cell with exactly 3 live neighbors becomes a live cell, as if by reproduction. And I guess that there is another rule that you can infer from all the above, and that is any live cell with 2 or 3 live neighbors will live to the next generation. So yeah, 2 or 3 neighbors is the best number of neighbors. Now to represent the cell in code, I'm using Rust, by the way. We can create an enum that can have 2 possible values, dead or alive. Now this is pretty cool, but you see we could represent dead or alive with only 1 bit. That is either a 0 bit or a 1 bit. But for this enum we need 8 bits because the minimum data type that we can use is an U8, and that means a byte. Since I have no idea what I just said, I found this crate that does all the work for me, fixed bit set, and this lets you have an array of bits. So it just means that we can have 8 times more the cells in our simulation, which was not a problem in the first place, but we are engineers and make things the hard way. Next, I stole some cool patterns from the Game of Life wiki and created some simulations that I can play in a time-lapse. But first I wanted to show some of the types of patterns. First one is a dot. It just dies, but with it we can build all sorts of shapes, so it is the most useful one. And in the file that I stole, it says that it was discovered by John Conway himself in 1969. Nice. Next one is a block. This one is just the larger version of a dot, but it doesn't do anything and is in some sort of an equilibrium. Each cell has 3 alive cells as neighbors, so it will just live forever. Now for the first pattern that actually does something, the blinker. This shape has 2 states and repeats them forever. So the idea is that the middle cell has 2 neighbors, so it will stay alive. The 2 edges will have 1 neighbor each, so both of them will die. And the other 2 edges, which are dead, have 3 alive neighbors, so they will come alive, and this will repeat each tick. One of the coolest types of patterns is the glider. This pattern works by crawling forward 1 step each tick. I guess you can try to figure out how it works by using the rules, but it's a bit too complex for me to try to understand it. And now for the best pattern, the most chaotic one. This is the Gosper glider gun, and it works by having 2 larger flying patterns that cycle between 2 blocks, and after they collide they generate a glider. And yeah, I guess you can tell why it's called a gun. And this happens every few ticks. Yeah, also imagine that someone really spent a lot of time in designing this thing. Probably someone as talented at Redstone as Mumbo Jumbo. Now there are all sorts of patterns like pulsars, sparks, 3C divided by 10 pi wave. Yeah, that actually is a name. But I mean, yeah, now I will just let you enjoy a time-lapse of some simulations. So yeah, this was today's video. If you are interested in the code, you can find it in the description. And yeah, also if you want to play around in the simulation sandbox, also check the link in the description to be able to play it. And yeah, I hope you like this project and see you guys next time.